Hi guys, welcome to day 3 of our AP Calc class notes. We've been talking a lot about limits of late. Limits help us with two big ideas in calculus. One is continuity, and the other is derivatives. We're focusing on continuity today. So our subject will be on continuity. You've talked about continuity in algebra 2 and pre-calc probably a little bit. Just as a reminder, we'll talk about continuity in layman's terms, in non-technical math terms. It's kind of like an unbroken line. Some people think of it as no jumps, no holes, no vertical asymptotes, things like that. So let's take a look at a couple of different types of continuity, discontinuities. When we take a look at these two graphs, what we notice is we see both of these two graphs have holes in them. We know about holes from P-Calc. When we have a hole in a graph, what do we know about the limit at that hole? Does the limit exist? For example, in the graph on the left, does the limit as x go to c exist? The answer is yes. How about on the right graph? Does the limit as x goes to d exist? Once again, the answer is yes. When we have a but they are definitely discontinuities. They are parts of the line where our function here is broken, right? These are called removable discontinuities. Removable discontinuities, what's unique about them is the limit exists. So we can say limit exists. But one of two other things are happening. Either the function is undefined, or the function is defined at a different point. So those are called removable discontinuities. And anytime we have a removable discontinuity, the limit is still going to exist, but either the function is undefined at that point, or the function is defined, but it's just at a different value than the limit is. Those are called removable discontinuities. Pretty simple. Our next one is called jump discontinuities. Think to yourself while I draw this, what do you think a jump discontinuity would look like? Was your prediction accurate? I hope so. Jump discontinuity, when we take a look here, the function just jumps up or down a level. Characteristics of jump discontinuities is, as you can see in both drawings, the left-hand limit and the right-hand limit both exist, or they're both numbers. However, they're different from each other. So jump discontinuities are, we can tell them by the left-hand limit and the right-hand limit are different. So now I would ask yourself, in this particular setup, in the graph on the left, does the limit as x goes to a exist? The answer is no, because the left-hand limit and right-hand limit are different. They both would give us a numerical answer, a non-infinite answer, but those limits would be different. If the left and the right-hand limits are different, then the limit does not exist. However, if we look back to our removable discontinuity, we can see that in our removable discontinuity, the left hand and the right hand limits are both the same, right? As we approach C and D from the left and right sides, they're approaching the same value, whereas in jump out discontinuity, they're not. There are a couple other discontinuities that are out there, but the last one that we're going to talk about is called an infinite discontinuity. Discontinuity. Think about what an infinite discontinuity might look like, and hopefully you'll predict the type of graph I'm going to draw. Infinite discontinuities occur at vertical asymptotes, where the left-hand and right-hand limits are infinite, not numerical, like in a jump discontinuity. So those are the three main types of discontinuities that we can have in a graph, and they're all just a little bit different, but in all cases, either the function is undefined at that discontinuity point, or it's defined differently than the limit. Okay, which brings us to our next important point. How can we define, instead of just having a term like no holes, breaks, jumps, vertical asymptotes, what's a mathematical way that we can use the notation and the symbols that we have learned previously in this course to help get an actual definition of continuity at a point? Taking a look at this graph that I drew, we can tell, ask yourself the question, is f of x, this function here, does it appear to be continuous at the x value of a? Well, as we look at it, do we see any holes at a? No. Do we see any jumps at a? No. Do we see a vertical asymptote at a? No. So we know the function is continuous at a. But for continuity to exist, we are going to talk about three classifications, three qualifications We're talking about three qualifications for f of x to be continuous at a point A, some made-up point A. Could be 5, could be 20. Who cares? Just any point A. Well, one thing that we know has to be true is we know that for a jump or an infinite discontinuity, those two places, the limits didn't exist. So we know that a limit has to exist. So our number one here is going to be, here we have 1, limit as x goes to a of f of x must exist. Now, this is step one, but step one we want to break down just a little bit more and think back to our previous lecture, I think two lectures ago maybe. For a limit to exist, that has qualifications of its own. It has two qualifications. The right-hand limit must equal the left-hand limit. So this isn't step two, this is additional to step one. So this is saying, AKA, the limit as x goes to a plus the right-hand limit, the limit as x goes to a plus, must equal the left-hand limit, the limit as x goes to a minus. So when we're working with piecewise functions, which we'll be doing shortly in this video, we need to make sure a limit exists, we must check both the right-hand limit and the left-hand limit. You can see in our picture here that both the right-hand limit and the left-hand limit at a, they're both approaching the same y value. So that's step one. The limit must exist. If a limit doesn't exist at a point, that function is not continuous at that point, and you don't even need to check steps 2 and 3. If a limit exists, however, that is not enough to say a function is continuous. Because take a look, I'm going to scroll back up. With our removable discontinuities, we have limits existing, but those two things, those two graphs right there, are for sure not continuous. Okay? So step one is very important here. The limit must exist. However, that's not enough to prove that something is continuous. The next thing we need is we need the function to be defined. So f of a must be defined. If f of a is undefined, then the function is discontinuous. If we take a look, scrolling back up at our removable discontinuity, the left graph here, the one on the left side of the page, f of c, we're using c this time, f of c is undefined. Therefore, there is no way that that graph is continuous because f of c was undefined. But take a look at the graph on the right. Our limit exists there. Our function is defined there. But clearly it's not continuous. So we have to think, we need a third step here for this case, a removable, a hole that's filled in somewhere else. We need a third case that's saying this. Not only must the limit exist at x as x goes to a, not only must the function be defined at a, but the limit as x goes to a of f of x must equal f of a. Now, sometimes people think of continuity just simply as the third step, right? You couldn't prove the third step to be true without having it with a limit that doesn't exist or a function that's undefined. Okay? So sometimes people like to skip to right to step 3, but I really want to focus on step 1 in terms of making sure something is continuous. Okay. Graphically, it's really easy to tell discontinuities because we just look for jump discontinuities, we look for removable discontinuities, or infinite discontinuities. But when we don't have a graph and we don't have our graphing calculators, it can be a little bit more challenging. I'm going to look at three piecewise functions, and we are going to determine if these functions are continuous or not. Take a look at this piecewise function. Just a reminder on piecewise functions, they're a function that uses different equations for different sides or for different numbers. In this particular piecewise function, we're using the function 4 minus 2x for all x values less than 1, and we're using 3x squared minus 1 for all x values greater than or equal to 1. Okay? So the question is f of x continuous at x equals 1? That's our question. Is f of x continuous at x equals 1? Now we want to go through a three-step process here to solve this. Step 1 is we have to show that the limit exists. So we want to know if the limit exists at x equals 1. I chose 1 because that's where the breakpoint is on this graph, right? That's where we switch from 4 minus 2x to 3x squared minus 1. On your AP exam, you may have to prove a piecewise function is continuous, and you're going to have to very thoroughly explain this. And you must show that the limit exists, and you must do it by using the right and left-hand limits. So let's start with the left-hand limit. So again, think back to when we did this graphically. When we wanted to do a left-hand limit, we were thinking of approaching the value 1, but from the left side of the graph, from the more negative side of the graph. I want you to think about the two functions we have up top. Which one of those two functions would we use for a left-hand limit? Would we use 4 minus 2x? Would we use 3x squared minus 1? And why? So pause the video and think for a second which one you would use. Okay, we're back. We want to use the function 4 minus 2x. Because that's the function defined for all the values less than 1. So that'll be on the left side of our graph. So to find the limit as x goes to 1 minus, we want to plug in 1 to our top function, 4 minus 2x. When we do that, we see that the limit as x goes to 1 minus is 2. 4 minus 2 times 1 equals 2. Okay. We're not done because we also have to check the right-hand limit. Now again, if I'm checking the right-hand limit here, I want to use the part of the piecewise function that is defined for the numbers greater than the x value that we're looking at, which is 1. So I want to plug that into the function 3x squared minus 1. What we notice here is that our right-hand limit is also 2. Now, what do we know if the left-hand limit equals the right-hand limit? Well, what can we jump to? We can jump to this statement right here. The limit as x goes to 1 of f of x equals 2. So our piecewise function passes qualification number 1. Okay? The next thing that we have to prove is step 2, which is that the function is defined. When we take a look at the function here, the function needs to be defined at 1. Ask yourself, is this function defined for x equals 1? And how do we know? Well, we know that x equals 1 is in the domain of this function because right there we see not only a greater than symbol, but a greater than or equal to symbol. So 1 is in the domain, so we need to also find f of 1. We have to make sure it exists, which we know it's going to. And now, although we already did this work for f of 1 equals, I just want to make it super clear which function we're using for f of 1. We have to use the value, the function 3x squared minus 1, because that's the one that's actually defined at 1. So let's plug it in and see what we get. We already did this for our right-hand limit, but again, on the AP test, you're going to need to be very thorough in your explanations. So now we know that f of 1 equals 2. So it's obvious now. The limit as x goes to 1 of f of x does equal f of 1, and that equals 2. So is the function continuous? Yes, f of x is continuous at x equals 1. Right, our explanation is in the work that we did. We showed the 3 steps for continuity. We showed the limit existed. We showed that the function was defined. And we showed that the limit equaled the function. Okay? So I really want you to run that through your head. Step 1, limit exists. Step 2, function's defined. Step 3, limit equals function at that point. Okay? I have 2 more examples for you. I'm going to put one example up. I'll have you pause the video, and then I will solve it for you. So the question here is f continuous at x equals 0? So again, is this function f continuous at x equals 0? What I want you to do now is I want you to pause the video and run through all 3 steps that we did in the previous one. See if you can do it on your own. Then I'm going to go ahead and solve this thing, and you can check your work. Okay, we're back. First thing we need to do is show the left-hand limit equals the right-hand limit to prove that the limit exists at x equals 0. So again, I need to choose the function 5x squared plus 1 for the left-hand limit because that's where x is less than or equal to 0. So I'm going to plug in 0. And I get the left-hand limit equals 1. Now I need to check the right-hand limit. For the right-hand limit, I need to use the function that's defined for x is greater than or equal to 0, and that's cosine. Please, 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 for the love of God, do not say that cosine of 0 equals 0. We know from pre-calc, from our unit circle, that cosine of 0 is 1. So again, because the right hand and left hand limits are both 1, we know the limit as x goes to 0 is 1. So we proved that the limit exists, which is probably the toughest part of a piecewise function. Now I just have to quickly show f of 0 So I'm going to show that f of 0 equals 1. Checking that is I already did that again. This time I did it on the left-hand limit. I need to use the one that has the actual equal sign with it. So I know that let me just make sure I did that right. Yep. So now again, now I know that yes, f is continuous at x equals 0. Okay, I'm going to have one more example, and then this video will be done. Now, predict which point am I going to ask about continuity at? 1, 0, 3. Yeah, obviously I'm going to ask about 3 because that's the place where the piecewise changes from 2x plus 5 to 2/3 x plus 1. So again, I'm asking the question, is f continuous at x equals 3? Go ahead and pause it. Try it, see if you can get it. I did my left-hand limit here. I have to use the function 2x plus 5 because that's where x is less than 3. And I got 11. Now let's try the right-hand limit. Trying the right-hand limit here, I see that I get my right-hand limit equal to 3. So right away I know that f of x is not continuous because limit as x goes to 3 does not exist. I know the limit does not exist because the left-hand limit and the right-hand limit are different. What I want you to think about now is what type of discontinuity do we see here? Is it a removable discontinuity? Is it a jump discontinuity? Or is it an infinite discontinuity? So pause and think. This is the last question. Okay, we're back. This is most definitely a jump discontinuity. The right-hand and left-hand limits are both numerical answers, but they're different from each other. If we looked at a graph of this thing, we'd see a big jump at the x value of 3. Thank you. Look for a video coming tomorrow as well.